A lot of stuff today. I'm just going to zip through this pretty quick. We're going to talk about techniques for doing this stuff, but we're not going to do as much math on the board. Just talk about how we do it. Go ahead.
Sorry if I call.
Yeah, go ahead, Stefan. Yeah. Okay, so what about this one then? So it says given a linear function with a slope of 4/3 and a y-intercept of -4. So if we wrote that in slope-intercept form, isn't that just going to be 4/3 x minus 4 mx plus b? Okay. But all they want us to do is draw a line on the coordinate grid to graph the function. Well, that's pretty easy, right? How do we graph a function in slope-intercept form? We start with the point that's going to be the y-intercept, right? So we start the line at 0, -4 at the y-intercept, and we make a slope triangle, right? We're just going to go up by 4 and over by 3 to get a second point, right? So we're just going to rise 4 and run 3 and get a second point, and then connect and extend. The other thing it wants is it wants a point on the line representing the x-intercept of the function. Well, we already got that, didn't we? Right? What if it wasn't so convenient, though? If I want to find the x-intercept is going to be where y equals 0, right? So if I plug 0 in for y, I would just get 0 equals 4/3 x minus 4. If I wanted to solve for x, I would add the 4, right? I'd multiply each side by 4/3. Or, oh, sorry, I wrote that backwards, didn't I? Huh. I add 4 and I get 4/3 x on this side, and I'm going to multiply each side by 3/4, right? And so I get the x by itself. My answer is just 3, isn't it? Well, I already can see that. It's right there. Okay. You get the idea. Okay, now how about this one? Which intervals on the x-axis, in which intervals on the x-axis are the functions decreasing? So indicate the intervals on the number line that represents where both functions are decreasing. So what this gets at then is what would the graphs be doing of those two functions? So we want to do a little sketch. You have graph paper available on SBAC, and I can't remember if you do on the SAT or not. They'll give you paper, okay. Okay, so this is the kind of thing where you'd want to make a little sketch, okay? So let's look at this function first, right? That's an absolute value function. So parabolas go with quadratic functions. They're used. What are absolute value functions? Let's go look at an absolute value function. Yeah, it's a v, right? Good, it's a v. It's got a vertex, just like a parabola does, but the vertex is the point of the v instead of the bottom of the u, right? Okay, so then this is in the form f of x equals, it's vertex form. It's a times the absolute value of x minus h plus k, right? Where h and k are just the coordinates of the vertex, and a is the vertical dilation factor, just like it is for a parabola. So for us then, what are the values of a and h and k? A equals 2, good. H equals 1, good, because we're subtracting 1. And k equals -4, good. Now how about this guy? Whoops, wrong color. How about that parabola? Okay, it's not written in vertex form, but if I want to get a sketch of this, all I need to know is what are the values of a and h and k, right? So this is in the form here. This is in standard form, isn't it? Right. So what are the values for g of x? It's in that form. What are the values of a, b, and c? -1, -2, and +8. Okay, if I want to sketch this thing, though, remember what our strategy was, right? We can't really sketch stuff from standard form, so we need to know what are the values of a and h and k. Well, we know a, but how do we find h? Okay, say it again.
B squared.
Not b squared. negative b, there you go. Negative b over 2a, right? So then all I've got to do is plug in, b is negative 2, so I'm going to get positive 2 over 2 times negative 1 is negative 2. So I got negative 1. And if I wanted to find k, all I'd have to do is plug it in, exactly. We're going to plug k into my or plug negative 1 into my function. And so I'd get, every place I have an x, I'd substitute in negative 1. And I'd get negative 1 squared is 1 times negative 1 is negative 1. Negative 2 times negative 1 is plus 2 plus 8, so I just get 9, right? H is negative 1, k is 9. Turns out I didn't really need to know what k is in this one, but I need to know what h is. So the coordinates of the vertex are negative 1, positive 9, and I can sketch both of these graphs now, right? So if I put these on an xy plane, where am I going to have room for that? How about right here? Okay, what about this guy? So the coordinates of the vertex are at 1, negative 4. So over 1, down 4. So there's the vertex of my b, right? My absolute value function. A is positive 2. So all that means that instead of going over 1 and up 1, I'm going to go over 1 and up how much? 2. There you go. So I'm going to go over 1, up 2, so it's going to be a little bit of a taller, more stretched out v, right? But the important thing to remember is that's happening, the vertex is where x is positive 1, right? Don't even really care about y, because all we're looking for is the intervals where the function is decreasing. So where is this function decreasing? The absolute value function. What's it mean for a function to be decreasing? What does the graph look like where a function is decreasing? It's going down. It's got a negative slope, so it's going downhill, isn't it, from left to right? So it's decreasing on this interval right there, isn't it? I don't include the endpoint. At the vertex, it's not increasing or decreasing. That's where it's making a change from one to the other, right? But everything to the left of 1, my absolute value function is decreasing. What about the parabola? Okay, the parabola has a vertex at negative 1, positive 9. So let's just say that's positive 9. So it's clear up here, right? Coordinates are negative 1, who cares? And is it opening up or down? Down, because A is negative 1. So instead of going over 1 and up 1, we're going over 1 and down 1, right? So it's going to look like this. It's just going to go. So where is that function decreasing? Isn't it decreasing every place to the right of the vertex, right? So it's going to be decreasing right there, isn't it? So we want the x values where they're both decreasing. So where they're both decreasing, now that's going to be everything to the right of negative 1 and to the left of positive 1, isn't it? That's the only places where both functions are decreasing at the same time. Everybody get that? Okay? So there it is. Okay? Let's do that. So what about this guy? This is a good one. So now we're given some function here. Here's what the graph looks like. I made it a little bigger. We want to mark yes or no next to each of these equations. Which ones of those represent the graph of that function? Okay, well, look at these first 3, right? These first 3 are in intercepts form or factored form, right? That's just a quadratic equation written in the form. All 3 of those are written in the form f of x equals a times x minus, you fill in the blanks here. Trace, what is this, remember? What forms are these? You get a times x minus, say it again, p times x minus q, right? Where p and q are the x-intercepts. So once again, this is what we call Hey.
I'm sorry to interrupt you.
Oh, you're fine.
This is your packet for next week for testing.
Gotcha.
Just be sure if there's a stone, kids that are like odd, ones that have to be set
Okay,
somewhere. And she said it on being Monday when you guys meet with Gil, so you might want to decide what this up to, because it's a rope, so.
Oh,
you
gotcha.
need someone to-
Yeah.
But I'll give that to Ken, so you guys can talk about that on
Okay.
Monday.
Perfect.
All right,
Thank you.
so much.
Sounds good. Okay, so this is, remember, this is what we call, this is factor form. Because it's factored, right? Yes, sir. Yes, you are. Yep, you bet. Okay, so it's factored form. The other thing we sometimes call it is intercepts. Oops. You know, this pen, I feel like it's like making me skinny. We're running out of virtual ink. That could be it. So it's intercepts form also. How come? Because it shows us the intercepts.
So small.
Right? That make sense? Okay? So factored form or intercepts form. So what are my x-intercepts? If I look up here, what are they?
-3.
-3, right? So we should plug, so P could equal -3. What about that one?
1.
+1. So we could call Q +1. So those are the values that we're plugging in for P and Q. Well, what's A? Positive or negative? Negative. If I'm going over 1 and down 1, what's A? -1. Okay, so then if P is -3, Q is 1, and A is -1, which of those three is the right answer? The middle one, yeah. Because look at that. That makes sense, doesn't it? I've got -1 times x minus -3 is x plus 3 times x minus 1, right? So that's the right one. Those two are wrong. Okay? Now what about the other forms down here? Well, those are vertex forms, right? We know that. Okay, so vertex form A times x minus h squared plus k. And the important thing there is that the vertex has coordinates hk, right? Well, what are the coordinates of the vertex here? Boy, it's like -1, 4. Everybody agree? So if h is, so that's going to be h. That's k. And a is still -1. So which of these is gonna work then? Bottom one, right? Because I get -1 times x minus -1 quantity squared plus 4, right? So there's my answers. Okay. Okay, so what about this? It says given the function y equals -x squared minus 2x plus 3, place a point on the coordinate grid to show each x-intercept of the function. Okay, well, there's a couple ways we could do that. One way we could do that real easily would be, we know that x-intercepts occur where y equals 0, right? So we could just set this whole thing equal to 0, right? So we could just do -x squared minus 2x plus 3 equals 0. Right? We'll set y equal to 0 and just solve that equation. And those will be the x-intercepts. So to solve that thing, what would we do? Wouldn't we multiply each side by -1 to make a positive, right? So if I multiply each side by -1, I'd get x squared plus 2x minus 3 equals 0. That factors, doesn't it? What are the magic numbers? Very good. 3 and -1. So what would my zeros be then? X equals?
-3 and +1.
Okay, so those would be my answers, right? The other thing I could do is I could put this back into that factored form or intercepts form, right? I could put it into the form y equals a times x minus p times x minus q, right? Well, if I'm starting with this, then what would I do? Then I guess I'm starting, well, here, I'm starting here. So y equals -x squared minus 2x plus 3. Well, I gotta know what a is. A is gonna be negative 1, isn't it? Right? Whatever the coefficient of x squared is, I gotta factor that out. So I'm gonna write this as negative the quantity x squared plus 2x minus 3, and we already factored that, right? That's x plus 3 and x minus 1. So isn't that telling us then that p is negative 3 and q is 1? Either way, right? Either way, we know that the x-intercepts are going to be at negative 3 and positive 1. And then it wants us to place a point on the coordinate grid to show the maximum value of the function, right? Well, the maximum value has to occur at the vertex, doesn't it? Right? This is a function, a is negative, so it's opening down. What's the value of h based on the graph?
3? No.
No. These are p and q. How do you know? Yeah, you can tell just by the graph.
Because there's two x's on the right.
Okay, so where would h be? That's the x coordinate of the vertex. Not 0. 0 would be over there. Negative 1, how come? Halfway in between, right? We gotta have symmetry, right? There's gotta be symmetry when we fold the line over the axis of symmetry. It's gotta overlap perfectly, right? 'Cause it's got reflective symmetry about the vertical line of symmetry. Okay, well, we can see right now, look at this, we can see that the line that splits those 2 points in half is the line x equals negative 1, isn't it? Well, I'll tell you what, in general, the axis of symmetry is always going to be given by this equation. The axis of symmetry is always just going to be x equals h. It's a vertical line through the vertex, right? The x-coordinate has to be the x-coordinate of the vertex, which is h. So this tells us right here that h equals negative 1. How do I find k if I know h? Plug it in. I'm finding a y value when I know an x value, so I'll plug it in. I can either plug it in here if I want to, or I could plug it in right here. Take your pick, it doesn't matter. I think we already did that anyway, didn't we? Well, I guess we did. That was the earlier one, yeah. So if I plug it in, how about if I just plug it in right here? Okay. If I plug in, okay, I should say. So k equals negative, and I'm plugging in h, which is negative 1 plus 3 times negative 1 minus 1. So that's negative 2 times negative 2. What is that? Positive 4. Right, I get that by just plugging h into the function. I could have just done it right there too. If I plug negative 1 in, I'm going to get 4, either way. So if I know k equals 4, then there's my point. Okay. Okay, what about these? So let's take a quick look at this example over here. There's not a lot of math to do, it's just interpreting this thing, right? The graph represents f of x, so I've got one parabola that's graphed, one quadratic function, and another quadratic function, g of x, that's given to us in a table, okay? Mark true or false by each statement. So they want us to know, first of all, is the line of symmetry of f of x, the blue parabola, x equals 5? It is definitely not. Look, there's x equals 5, would be the vertical line through x equals 5, and that doesn't go down the middle of the parabola, does it? So the answer is false. Is the value of x where f of x is at its maximum? So f of x is at its maximum. The value of x when f of x is at its maximum. Well, what is the x coordinate up there? It looks like it's you can't see it, but it's like 2.5. We don't even care about the y coordinate, right? If that's the x coordinate when f of x is at its maximum. Well, is that greater than the value of x when g of x is at its minimum? Where is g of x at its minimum? There's the inputs, there's the values of g of x. It looks like 3 is the lowest value for the function, the lowest y value, doesn't it? So that's gonna be right there, right? Well, what's greater? Is 2.5 greater than -1? Yeah, so that's true then, isn't it? Right? And then last one, the function in the table g of x, it says the function g of x does not have any real x-intercepts. True, how come? It doesn't reach 0, does it? Because it would go through the x-axis when y equals 0, and it never does that, right? The smallest y value is still positive. And so that's false. Oops, no, it's true. All right. It doesn't have any real x-intercepts because it never goes through 0. Okay? All right, very quickly, you tell me real quick. Oh, come on now. Does it make sense here? How would I find the equation for the line of symmetry for this function? Remember, line of symmetry is just going to be x equals h, right? H is negative b over 2a. Well, that's going to be -12 over 2 times -4 is -8. Well, that's 1.5, right? How about here, in 2 seconds? What's the equation of the line of symmetry for that parabola? X equals 6, right? Because that's h, right? It's x equals h, okay? Okay, what about these? So it says choose the appropriate box to indicate which equation goes with which table, okay? Well, now let's look at these. Each of these tables you're putting in the same x values. These are the functions that we're plugging values into to get y, right? Well, if you look at these functions, look what's going to happen if we plug 1 into each of these. Oops. I'll just do this. Let's see why this is true. So if I take this function right here, f of 1 equals 2 times the square root of 1. What's that? Two times the square root of 1. What's the square root of 1? 1. So that's 2. Right? How about this one? If I do f of 1, I'm going to get 1 times the square root of 2, which is the square root of 2. And what about that one? F of 1 equals the square root of 2 times 1, which is the square root of 2. Now, if I put 1 into all those, I got the same answer back every time. Actually, if I put 0 into all those, I got 0 back. So 0 wasn't very helpful, but 1 was. Because look at this. That's the one that has to go with this equation, isn't it? Right? So table C, we know, has to go with that equation. Okay, now what about the other two gave us the same answer back when we plugged in 1. We could plug in other values, but we could even be tricky about this in a different way. Look at this function right here. So if I've got x times the square root of 2, that's the same thing as the square root of 2 times x, right? How about this function right here? The square root of 2x. The square root of a product is equal to the separate square roots. I can break that up into separate square roots if I wanted to. So earbuds should be all out right now. I shouldn't see any earbuds out there. So the square root of 2x is the same thing as saying the square root of 2 times the square root of x, right? So the purple function, we end up with the square root of 2 times x. The green function, we get the square root of 2 times the square root of x. In both cases, we're multiplying x by something, right? Or we're multiplying the square root of 2 times something. But what's going to be bigger, x or the square root of x? X is, isn't it? Right? So we know that this is going to be the bigger of the two. Even though, and we can see a trend here, can't we? If we look at these other ones, they start off 0 and 1.41, but from that point forward, every value of the function is bigger in table A than it is in table B, isn't it? Right? Everybody see that? And so even though none of those are very convenient values to plug in, we can still see that this function is always going to be, the purple function is always going to be bigger than the green function when we have values bigger than 1. You could even sort of cheat on this and say, well, what if we plugged in a really convenient value? Like, what if we plugged in something like 8? If I plugged in something like 8, I'm going to get the square root of 2 times 8 is the square root of 16, which is 4, right? But if I plug in 8 up here, I'm going to get 8 times the square root of 2. Well, that's a lot bigger than 4, isn't it? Everybody agree? The square root of 2 is bigger than 1, right? Times 8 is something bigger than 8. If I plug in an 8 down there, I just get back 4. That's pretty small, right? So you just got to figure out which one's bigger, okay? That's the way you think about those. Okay, what about this guy? So we're looking at some modeling here. Okay, different topic. So Robert's making a rectangular pool. The length of the pool is 6 feet greater than its width, which is W, in feet. Write the function f of W, which describes the area in square feet of the pool. So all you need on these is maybe a picture, right? And it really helps to have a picture. So if I'm saying that the width is W, what's the length? It says it's the length of the pool. The length of the pool is 6 feet greater than its width. W plus 6. Right? So doesn't that mean that the area is just W times W plus 6? Okay, no biggie. Okay, this one down here, the reason I wanted to draw this to your attention is because a lot of times on standardized tests you'll get questions about average speed. Okay? It's something that we can relate to, but you have to calculate an average, right? So average speed is nothing more than total distance over what? How do you calculate speed?
Distance over time.
Distance over time. Just total distance over total time, right? So when you're trying to build an average speed from some information, you know you're just going to take a fraction. Where on the top, you've got to account for all the distance traveled, and on the bottom, you have to account for all the time traveled, right? Well, there's two parts to this one. Okay, it says, Peter traveled 425 miles during the first 6 hours of his trip. Okay, so there's a distance and a time, right? So it means he traveled 425, so that's going to go on the top of the fraction. That's part of what we're adding up on the top of the fraction. On the bottom, we've got a 6. There's another part of this, though. Okay, it says, Peter traveled at a constant speed of 65 miles per hour for the remainder of the trip. Write the function f of h, which describes the average speed during the entire trip as a function of time, h, in hours. Peter traveled after, so h represents the time in hours he traveled after the first 425 miles. So h only represents the time for the second part of the trip. So for the second part of the trip, there's the rest of the total time. 6 hours for the first part of the trip, h hours for the second part of the trip. How far did he go, the second part of the trip? If he's traveling at a constant speed of 65 miles per hour for h hours, how far did he travel? 65 miles per hour times h hours means you go how far? 65 times h, right? Make sense? Okay, so there's the two parts of the distance. First part and second part, there's the two parts of the time. First part plus second part. That's it. Okay? Okay, what about this? So this is kind of a confusing wording on this a little bit, but you just got to read through this, and a lot of times you just got to power through the words and just take your time and extract the meaning from this. It's about concentrating and taking your time. So if x equals n, then y equals z is a solution of the equation represented by the graph. What is the approximate value of n when z equals -2? Well, z is just the y value, isn't it? So all they're asking for is what's gonna be the x value when the y value is -2? That's easy enough, right? -2. There's the line y equals -2. And so we're just looking for the place on the function where y equals -2, the place that has a y coordinate of -2. Well, what's the x coordinate there? It looks like it's -7. Done. Right? We did a lot of stuff like that earlier, with graphs. Okay, what about this one? They think they're being really tricky on this, but we can handle this, no problem. The graphs of the functions f and g are shown where it tells us what each of these things are. Okay, it makes you think you're going to have to do a bunch of algebra, but you don't. Keep reading. Choose the two closest approximations for solutions to the equation f of x minus g of x equals 0. Well, that looks complicated. F of x minus g of x equals 0. But isn't that the very same thing as saying f of x equals g of x? Right? When would f of x minus g of x equal 0? When they're equal, right? Algebraically, that means you're just adding g of x to the other side of the equation. Either way, you end up with f of x, that's the green function, equals g of x, that's the purple function. Well, you tell me, how would I find the x values where f of x, the green function, equals g of x, the purple function?
If we just use the same thought process on the zero product, like try to make it 0.
Okay, but we don't have to be that tricky. What did we always do? If we're trying to find out where functions,
Just plug it in.
yeah, right? We know that functions are equal when they intersect, right? When you say plug it in, I'm assuming that's what you're talking about, right? So if we want to know, like, that's how we solve linear systems graphically, isn't it? If we want to solve a system graphically where we have, you know, y equals this function and then y equals this function, didn't we just graph the two things and look where they intersected, right? So if I want to know where the functions are equal, I'm just looking at the intersections, and there they are, right? What are the x coordinates of the intersection? Well, this one looks like it's at 4.5 something, who cares? And this one looks like it's at -4.5 something, who cares? So the answers are there and there. Okay? Right? So you just got to think about an easier way to look at this. We're looking for intersections of curves. There'll probably be a lot of questions like that. Okay, we'll skip this one. Okay, last one before we jump into SOHCAHTOA, which may not get to today. So this is just quick review of linear inequalities in two variables, right? We know that that this graph goes with a boundary line and a shaded half plane, doesn't it? Right? That's what we get when we graph a linear inequality that's got x's and y's in it, okay? So how did that work? Well, if we want to come up with the equation of that boundary line, we just look for, what is the equation of that line? Can you see can we see m and b out of this? What's b? What's the y-intercept? Okay, so there's 0, -4. So b equals -4. And it looks like I could just use maybe a slope triangle where I'm going to rise by 4 and run by 2. So what's the slope? 4 over 2, right? Rise over run. So that's 2. Okay. So then we end up with the boundary line is y equals mx plus b, so 2x minus 4. But we don't want an equal sign there because it's not a line. It's an inequality. So what's going to go there? Well, first of all, do I have an equal sign with my inequality?
No.
No, I don't, because it's a dashed one. It's not solid, right? So we're not including the boundary line. It's just a boundary. Now you tell me, is it going to be less than or greater than? Is y less than or greater than the boundary line in the shaded region? Less than. How come? It's below. Yeah, y values below are y values that are smaller, aren't they? Right? So it's going to be y is less than 2x minus 4. Okay? If I want to solve a linear system where I've got more than one inequality at a time, remember all that is we're just going to solve for y, so y is going to be greater than, what, did they give us, I don't remember, did they give us on this one, No, they didn't. Never mind. So y is greater than, if I add the 4x to the other side, y is greater than 4x. Well, y is greater than 4x, there's the line y equals 4x, so it's going to be everything above that steep line, right? Okay, what about the bottom one? What about here? If I solve for y this time, I could subtract x. So I'm going to get negative x plus 6 on the other side. That's a negative 2y, isn't it? Divide each side by negative 2. And I get y. I'm going to get negative over negative is positive. I'm going to get, so that becomes a 1/2 x. And 6 over negative 2 is negative 3. I've got to flip the sign around. So I get y is less than 1/2 x minus 3. That's the line that's not very steep. So we're shading below that line and above this line, and that's the only region where both places are shaded at the same time. So that's my solution, right? Okay, last thing that we're going to kind of start on tomorrow. Do you guys remember SOHCAHTOA?
Gosh.
Okay. SOHCAHTOA. So you get a lot of mileage out of SOHCAHTOA, I promise you. This is super easy stuff, and you get a lot of correct answers from this. So let's just quickly, let's define, if I've got a right triangle, and I'm going to call that angle theta. Well, in terms of theta, what are going to be, which one of the sides in that triangle is the hypotenuse? Okay, so the one opposite the right angle, right? So that's my hypotenuse. If that's the angle that we're working with, what's the opposite side? Okay, over there, right? And how about this would then be the adjacent? Adjacent means next to. Okay, so then what is this telling us?
Make sure you wear your shorts and get a short stack of buckaroo pancakes before school at the buck stop. Go Bucks.
Okay.
So sine theta is the ratio of opposite over hypotenuse, right? We know that cosine of that angle is equal to the ratio of adjacent over hypotenuse. There you go. So, okay, make sense? Okay, we'll pick that up tomorrow. Good job.